Hey everyone, and welcome to section 8.7, the last section in chapter 8 on roots and radicals. In this section, we're going to be talking about using radicals in functions. So, as you might expect, a radical function is a function that's defined by a radical expression. Okay, so mathematicians aren't great at naming things, but at least they're consistent. So we want to keep in mind some of the restrictions as far as domain is concerned. Whenever I'm taking an even index root, the radicand has to be non-negative. When the index of the radical is odd, the radicand can be any real number that you like. When involving radicals and functions, you're going to kind of naturally have to fuss over domain a little bit. So let's look at this example here. I know that I have to have my radicand, which is in this case 3x minus 4. It has to be non-negative because I'm taking a square root. So I need to have 3x minus 4 is greater than or equal to 0. Hey, linear inequality, all right. It's a callback. So if I add 4 to both sides, I have 3x greater than or equal to 4. And divide both sides by 3. I'm dividing by a positive, so I don't have to switch the sign. So we get x greater than or equal to 4 over 3. So that is a set that describes the domain of the function f of x. Of course, if I want to write it in interval notation, I am writing the set of all x that are greater than or equal to 4 over 3. So I have 4 over 3, and everything greater than that. And since it's a greater than or equal to, I can include the endpoint of 4/3. All right, now for the function g of x equal to the square root of 6 over x minus 1, let's just take a crack at evaluating this function at a given point. So we're going to evaluate g at 25. So g of 25 is going to be equal to the square root of 6 over 25 minus 1, which is equal to the square root of 6 over 24. That is equal to the square root of 1 over 4, because 6 over 24 reduces, and hey, 4 is a perfect square. So I get 1/2. I want to write the domain of this function in interval notation. So there are a number of things to watch out for here. First of all, I need the radicand to be non-negative, right? So in other words, I need 6 over x minus 1 to be greater than or equal to 0. But honestly, since 6 is fixed, it's never going to influence the sign of this radicand. So really, the only thing that I have to worry about is when the denominator is negative. So in other words, I want x minus 1 to be greater than or equal to 0, because that's when the denominator is going to be non-negative. So x greater than or equal to 1. Okay, if I want my radicand to then be non-negative, it has to be greater than or equal to 1. But we have a caution here because we also have a denominator. In that denominator, x minus 1, if I were to plug 1 in, I would get 6 over 1 minus 1. I would have division by 0, which is a no-no. So actually, this function's not defined at 1, meaning when I write down my domain, which is everything greater than, so we'd have the interval from 1 to infinity, I can't include 1 in my interval. So I don't have my endpoint, it's with parentheses. The next thing that we want to do as far as radical functions are concerned is sketch them a little bit. So, of course, when we graph radical functions, we need to know the domain, because we need to know where the picture lives. After we figure out what the domain is, we're going to plug in a bunch of values that are in the domain to create a guess at what the graph looks like. It's not going to be exact because there's no way to collect that much data. But okay, let's look at an example. So for the function f of x equals square root of x minus 2, we want to find the domain of the function, we want to graph the function, and then we want to use that graph to determine the range. So for my domain, the radicand has to be non-negative, so I need to have it that x minus 2 is greater than or equal to 0. Well, that's an easy inequality to solve. X has to be greater than or equal to 2. In interval notation, that would be close bracket 2 comma infinity. I can include 2 because there would be no division by 0 or anything strange like that. Now I want to graph the function. I'm going to need my graph paper here. So here's my graph paper. I'm just going to also keep track of what we've already done. So our domain is 2 to infinity, including 2. Now I want to graph the function. So I have to pick out a bunch of x values that are greater than or equal to 2. Right now I can't plug in 0 here because it's not in my domain. But I can plug in 2. So if I plug in 2, I'll have the square root of 0, which is 0. So the point 2 comma 0, let's graph that. Okay. And let's see, what to pick next? Well, I want to pick points so that when I subtract 2, I end up with a perfect square. 3, for example, would be a good one, because when I take 3 minus 2, I get 1, which is a perfect square. So let's graph that, 3 comma 1. Let's see, what else? I can do 6. And how about 11? So if I plug in 11, we get square root of 11 minus 2 is equal to the square root of 9, which is 3. Starting to take shape a little bit. And 18. Square root of 18 minus 2 is the square root of 16, which is 4. All right, now let's see if I can graph this guy. I don't think I'm going to get too many other points on these axes. So I'm going to connect all my dots. And that's a graph of, well, a guess at the graph of my function y equals square root of x minus 2. Now when I use the graph to determine the range, it's kind of hard to do from so little data, but you can see that this function keeps going up and up and up. If I wanted to get it to a value of 5, I would need to plug in 27, which would give me the square root of 25. And I would need to plug in 38 to get a value of 6, and so on and so forth. But it is going upwards. So we just have to, if there's a positive value, this graph will get there eventually. So the range of this function, which is all of the y values, basically anything on this side the y-axis this graph could hit. That would make it 0 to infinity closed. And that about wraps it up for section 8.7 and chapter 8 in general. Where are we going from here? Looking towards the future, we're going to be talking about more deeply about quadratic equations and functions. We'll talk about the quadratic formula, for instance, and then after that, we're going to be going into exponential and logarithmic functions, and that takes us to the end of the class. So there's a light at the end of the tunnel.